The first step is to write the matrix in the determinant form. Okay, in the determinant form by this way, giving a little bit wider space. Okay, giving a little bit wider space, 1 minus 1 minus 1 and 1. Okay, and after writing the matrix in the determinant form, then from the diagonal, from the first diagonal, subtract with lambda. Okay, you have to subtract with lambda from the first diagonal, and it will be equivalently written by this way, minus lambda I in this form. So that is called the characteristic equation, and put this characteristic equation equal to 0. So the first step is to write the characteristic equation. So that's how we are writing the characteristic equation. So we will write the same matrix in determinant form and subtract lambda from the first diagonal. So that is called the first diagonal. Okay, this is called your first diagonal. Okay, so only you have to subtract the lambda from the first diagonal. Done. And after that, you already know the process of solving the determinant, because this is the determinant, a 2 by 2 determinant. So what we'll do in determinant, we multiply first diagonal. So we multiply first diagonal, and with the reverse sign second diagonal. Minus minus plus, the reverse sign is minus 1. Minus 1 multiplied by minus 1 is 1. So answer equal to 0. Okay, minus 1 multiplied by minus 1, answer is plus 1. So we will write minus 1, the reverse sign. Okay, so that's how we solve the determinant all the time. Now we will try to solve. So 1 multiplied by 1 is 1, minus lambda multiplied by minus lambda is plus lambda square, minus multiplied by 1 is minus lambda, 1 multiplied by minus is minus lambda, minus 1 equal to 0. So lambda square minus 2 lambda, and minus plus cancelled, so it equal to 0. This minus and this plus and minus cancelled. So taking sub lambda out, lambda minus 2 equal to 0. So lambda equal to 0 and lambda is equal to 2. So two eigenvalues have been identified. So these are called the eigenvalues. The first step is completed. Eigenvalues have been identified. So now we are moving towards finding the eigenvector corresponding to these eigenvalues one by one. So first of all, we will find lambda is equal to 0. Okay, what we need to do, we'll write the same determinant matrix in the form of determinant. Whatever we have, the matrix that has been written in the form of determinant, we will write again. Okay, in the form of determinant. So 1 minus lambda, 1 minus 1, I think it should be 1 minus lambda minus 1 minus 1, 1 minus lambda. So you should write that determinant in the form of matrix. Okay, and then you will write C1 and C2 and equal to 0 0. Okay, for lambda is equal to 0, we would replace the value of lambda. Wherever you find lambda, replace with lambda is equal to 0. So 1 minus 0 is 1, minus 1, minus 1, 1 minus 0 is again 1. C1 and C2 and equal to 0 0. So the last 0 0 will remain 0 0 for all type of eigenvalues and eigenvector questions. The last column 0 0. Okay, so all eigenvalues and eigenvalues question will have the last, this column will be 0 0 in any case. Okay, so we'll keep 0 0 all the time. And what we have to do now, we have to write the augmented matrix the way I told you. This is the application of linear independence. So first of all, we have written the way we write in the linear independence, and then we would write the augmented matrix 1 minus 1 0 minus 1 1 and 0, separating by dotted line. Now we will apply the row operations, very famous row operation. Our objective is to convert this minus 1 to 0. So when we want to convert this to 0, I think you are already familiar with the row operation. What I have to do? The reverse sign of this is plus 1. So plus 1 multiplied to each element of row 1 and will be added. Okay. So plus 1 and minus 1, answer is 0. Plus 1 multiplied by minus 1 is minus 1. Plus 1, answer is 0. And 0 will remain 0 here. So what I did, I simply add row 1 with row 2. Okay. So the first column is representing, since all the values are 0, so we cannot extract any C1 or C2 from the second row. So the only option is row 1. So the first column is representing C1. So C1 minus C2 equal to 0, because that element is representing C1 and the second one is representing C2. Okay. So C1 minus C2 equal to 0. Sorry. And C1 can be written as C2. Okay. C1 equal to C2. If C2 equal to T, then C1 equal to T. So it means that C1 and C2 have two values, C1 equal to T and C2 equal to T. If we take the T out, 1 and 1. Okay, so that is called the eigenvector, corresponding to lambda is equal to 0. So this is the eigenvector corresponding to lambda is equal to 0. And similar way, we will proceed to find the eigenvector corresponding to lambda is equal to 2, because we have identified two eigenvalues. So for the second eigenvalues, lambda is equal to 2. Okay, we would write again the same determinant part in matrix. Okay, so 1 minus lambda minus 1 minus 1 1 minus lambda. Okay, again C1 C2 and again 0 0. So now we will be replacing a lambda is equal to 2 wherever we identify lambda. So 1 minus minus 2 minus 1 minus 1 and 1 minus 2. So wherever we have identified lambda, we have placed 2, not minus 2. It should be 2. Let me check again if it is correct. Yeah, it is 2. So we have placed a value which is 2 against the lambda. C1 C2 0 0. So 1 minus 2 is minus 1 minus 1 minus 1. 1 minus 2 is minus 1. Okay, and C1 C2 equal to 0 0. Okay, so now we will write the augmented matrix again. So minus 1 minus 1 0 minus 1 minus 1 0. By taking out the minus from row 1, we can have 1 1 0 minus 1 minus 1 0. So now simply adding two rows, row 1 with row 2, we can have 1 1 0 0 0 0. Okay, so it means that C1 is equal to minus C2 because C1 plus C2 equal to 0. Okay, so it means that C1 equal to minus C2. So if C2 equal to T, so then putting the value of C2 in C1 is minus T. So it means that C1 C2 equal to minus T and plus T. So if you are taking T out, minus 1 and plus 1. So that is called the eigenvector corresponding to lambda is equal to 2. So this is the eigenvector. Okay, so that's how the question is completed. So the first part, the finding the eigenvalues, is the application of determinant, and another part, finding the eigenvector, is the application of linear independence. Okay, shortcomings. So we multiply these algebraic expression. So 1 multiplied by 3, answer is 3, minus lambda multiplied by 3 and minus lambda multiplied by 1, so 4 lambda, and minus minus plus is lambda square, minus 8 equal to 0. So minus 8 plus 3 minus 5, so we can write lambda square minus 4 lambda and minus 5 equal to 0. So solving this algebraic quadratic equation, we just factorize. It's very simple method. Minus 5 plus lambda minus 5 equal to 0. So minus lambda is out, lambda minus 5 plus 1, lambda minus 5 equal to 0. So lambda plus 1 and lambda minus 5 equal to 0, and lambda equal to minus 1 and lambda is equal to 5. So two eigenvalues we have obtained, and now we are moving for eigenvectors. Eigenvectors for lambda is equal to minus 1. So I told you just to write the characteristic equation in matrix form. So 1 minus lambda, 4, 2, 3 minus lambda, C1, C2, and last column will be 0 all the time. And now you just need to put the value of lambda inside this characteristic equation. So 1 minus minus 1, 4, 2, 3, 3 minus minus 1, C1, C2 equal to 0 0. Okay, so minus minus plus, so 2 4, 2 minus minus plus 4, C1 C2 equal to 0 0. So what we can do, simply you could write in the augmented form 4 0 2 4 0. That's how you should write here. So if you subtract both of these rows, if you do R1 minus R2, so even if you don't put convert this 2 to 1, you can get 0 zeros down. Okay, but it is if it is up to you, it's depending upon how you think about the row operations. So for example, if you follow the process which we were following earlier, so simply divide row 1 by multiply by 1 by 2. Okay, so steric is the multiplication. So 1 2 0 2 4 0. So that should be obtained. After that, the leading element is 1, the reverse of 2 is minus 2. So 1 2 0 will remain the same. reverse of 2 is minus 2, multiply by 1, minus 2 plus 2, answer is 0. Minus 2 multiplied by 2 is minus 4, plus 4, answer is 0 and 0. So you have applied 2r1 minus r2. So it means that C1 plus 2C2 equal to 0. Okay, C1 plus 2C2 equal to 0. It means that C1 is equal to minus 2C2. Okay, so if C2 equal to T, then C1 equal to minus 2T. So it means that C1 C2 equal to minus 2T and T, and T will be out, minus 2 and 1 is the eigenvector. So you will apply the similar method to get the second eigenvector. Okay, so now I'll proceed to test. That is better, how do we apply the testing of the eigenvalues and eigenvector. So eigenvector is represented by x. Okay, eigenvector is represented by x. So the formula is ax is equal to lambda x. Ax is equal to lambda x. So ax is equal to lambda. What lambda we have identified initially? The one we have found the eigenvector. It's a minus 1, for which we have found the eigenvector. It's a minus, it's minus 1. So it means that in this expression we put minus 1, and x is whatever your eigenvector, minus 2 and 1, and you have a. So whatever the matrix name, so A is representing your matrix, whatever given matrix. So here it is B, so simply write B. Okay, so B is 1, 4, 2, 3, and it should also multiply by x, which is minus 2 and 1. So minus 1, minus 2, 1. Okay, so in that case we have both right hand side and left hand side. Okay, so this is called the left hand side and this is called the right hand side. So we will pick one of the side. We will pick right hand side to get the, this is left hand side. Left hand side. So we will pick the left hand side to get the right hand side. So left hand side is picked, which is 1, 4, 2, 3 multiplied by minus 2 and 1. So we already know the process of multiplication. Each row multiply to column. So 1 multiplied by minus 2 is minus 2. 4 multiplied by 1 is plus 4. Okay, and then for the second row multiply again to the column. 2 multiplied by minus 2 is minus 4. 3 multiplied by 1 is plus 3. Okay, so we are getting answer which is 2. Minus 2 plus 4, answer is plus 2. Minus 1 and 3, answer is minus 1. Okay, now we simply could take out the minus 1 and have minus 2 and 1. Okay, so which is exactly the same right hand side. Okay, so it means that the eigenvector we have identified is accurate. Okay, so because we starting from the left hand side and got the right hand side. So that's how we can test, just a simple multiplication of the matrix with your eigenvector. So your given matrix, when multiply with your eigenvector, you should get the lambda x. So now I'm stopping the